Welcome to day 8, holes. We're going to do more rational functions, but we're going to add a new feature today. So the 4 features that we did last time in rational functions were an x-intercept, where we just use x equals 0, and that always gives me the y-intercept. The x-intercepts, that's when the numerator was equal to 0, so we might have to factor. The vertical asymptotes was when the denominator was equal to 0 after we factored, and a horizontal asymptote was when we did leading term over leading term, and we usually got some number like y equals 2 or y equals -3 or sometimes even y equals 0. So this is a problem that we did yesterday, and I already have it factored, which makes it a whole lot easier. But let's go through these 4 features that we have above and using our rules to figure out what those values are. So we did all these features, the y-intercept using x equals 0, the x-intercepts come from the numerator, the VAs come from the denominator, and our horizontal asymptote is leading term over leading term. We got our red dashed lines for the asymptotes and the blue dots for the intercepts. And the one in the middle has to start up by infinity. Oops, I got it. Goes by infinity. X-intercept, y-intercept, down to -infinity. The one on the right has to go through the x-intercept, so it's going to start by infinity, x-intercept, and then level off to -3. And the one on the far left, since there are no dots here on the x-axis, I cannot go through the x-axis whatsoever, so I have to be like this, level and then down to -infinity, if you recall that from last class. So here's a new function, another rational function, and let's see what happens when I plug 3 into this function. So g of 3 is going to equal to 3 squared minus 9, 3 squared minus 4 times 3 plus 3, and I do some simple calculations on the bottom. I get 9 minus 12 plus 3, and I get 0 over 0. Oh, we did this with limits. I'm not happy. I do not like 0 over 0. Remember, it doesn't tell you anything. So what's going on with 0 over 0? So the idea is, what does 0 over 0 look like on a graph? Well, 0 over 0 on a graph is basically this. 0 in the numerator was an x-intercept, which is just a dot on a graph. 0 in the denominator was a VA, which was a dashed line on a graph and actually was missing values. So my question is, how can it be both? How can you be a dot on the graph and a dashed line which is a missing value on the graph? So this is our conundrum. So 0 over 0. This is what's going on with 0 over 0. 0 over 0 is a hole in a graph. Basically, it's a dot on the graph, but it's a missing dot on the graph, if you get what I mean. So this is our 5th feature, but we will do it first, because I think I should know when I have a hole and when I don't have a hole. So again, we would need to factor, and then we're going to cancel some things out, just kind of like we did with limits. It's exactly the same. We factor things out and we cancel what are identical, and then we move on from there. So what we're going to do, we want to identify the hole or holes in these functions. Not only the x value of the hole, but also the y value of the hole. So what I need to do is factor. I'm going to take a negative sign out of here, and I get x squared minus 2x minus 3, because I do not like factoring negative x squared, and I just have x squared plus 4x plus 3. And then I'm going to factor some more. I'm going to get my negative sign, x plus 1, x minus 3 on top, and on the bottom is going to be x plus 1, x plus 3 on the bottom. So this is what we're getting. This is the whole key to this process. We're seeing identical factors. We're seeing that these two are identical. So they're going to cancel out. And what does this mean? We have a whole at this x value. This is x equals negative 1. That's what we get. Well, what's left over? Well, what do we have left over after things cancel, just like limits? We get what's left over, and that's our functions left over, except now I need to find the y value. So how do I find a y value? I take this x value, I plug it in to find the y value. So the y value for the whole is going to equal, well, when I plug in negative 1, I get negative of negative 1 minus 3 over negative 1 plus 2. I get negative of negative 4 over 2, which is equal to 2. So I get a y value equal to 2. So the actual whole, in the graph is at the point negative 1 comma positive 2. X was negative 1 from the canceling and factoring. I plugged what was left over, and I found out that y was equal to 2. I think this one's going to have a lot more factoring than the other one. So let's see what we get here. We get, take an x out here, I get x squared minus 16. I'm going to take a negative 3x out of here. I get x squared plus x minus 12 on the bottom. I'm going to factor some more. I get x plus 4, x minus 4 on top. And on the bottom, I still have my negative 3x, but I get an x plus 4, x minus 3 in the denominator. Except now I can see a few things cancel out. These x's cancel out, which means I have a whole at x equals 0 because of these x's, but I also have another whole with these x plus 4's canceling out. I have another whole at x equals negative 4 because these x plus 4's cancel out. So what am I really working with? Well, I'm working with what's left over. When I cancel those things out, I'm left over with x minus 4 in the numerator, and don't forget I have a negative 3, x minus 3 in the denominator. So that's what I'm going to work with. Now I have to find the y values. So the first thing I'm going to do is plug 0 in to find the y value, and I get negative 4 over negative 3 times negative 3. I get negative 4 over 9. So I have one whole at 0 for the x and negative 4 over 9 for the y value. And then I'm going to do the second whole. I'm going to plug negative 4 in here. I get y equals negative 4 minus 4 over negative 3. Negative 4 minus 3. I get negative 8 over negative 3 times negative 7. So I get a y value of negative 8 over 21. So the second whole that I have is at the x value of negative 4 and the y value negative 8 over 21. Those are the two holes. Sometimes you could have more than one hole. You have two holes on that graph. So I really have 5 key features to a rational function. The first one, well, I'm going to have to factor a lot, but I should always do the whole first. The whole is when I get that 0 over 0. Again, I'm not happy about it, but then what I'm going to do, I'm going to factor. And what I should get the same factor over the same factor. And what should happen is that these two cancel out. Let me grab pink. These two cancel out. And this should be the x value of the whole, and then what I need to do plug x into the rest of the function to find the y value. Okay, so that's the hardest part, finding the whole. After that, we still have the same rules as before. My x-intercept is when x equals 0. My y-intercept is when x equals 0. My x-intercept is when the numerator is equal to 0. My VAs is when my denominator is equal to 0, and my horizontal asymptote is still leading term over leading term. That has not changed. So we're going to do the same graphs that we did yesterday, except we're going to do this fifth feature, finding the hole in the graph, and probably doing that first. Well, I should always factor my rational functions first. X minus 3, x plus 3, x minus 3, x minus 1. Things cancel out, which is good that they cancel out. And what's really left over, what I'm really working with, is x plus 3 over x minus 1. That's what I'm really going to work with. Okay, those other things cancel out. Well, because they cancel out, that means there's a hole at x equals 3. So I need to find the y value for the hole by plugging in what's left over, the rest of the problem. So the y value is going to be by plugging 3 in there. 3 plus 3 over 3 minus 1, or 6 over 2, which is 3, which tells me I have a hole at 3, 3. X was 3, and it just happened to be that y was also 3. Now when I want to do my y-intercept, I could plug it in the beginning of the problem. I could plug 0 in the beginning of the problem, or the stuff that's cleaned up. Either way, I'll just plug in the beginning. I get negative 9 over 3, so I got my y-intercept of negative 3. My x-intercept comes from the numerator. I'll keep it blue. From what's cleaned up, not at the beginning of the problem, over here, and that's just going to be x equals negative 3. My VAs come from the denominator. Again, that's from what's cleaned up. The rest of the problem, I just have x equals to 1. And then finally, when I want to do a horizontal asymptote of leading term over leading term, I could do it from the beginning of the problem, x squared over x squared, which is equal to 1, so I get y equals to 1. If I want to be more detail oriented, I could say my numerator was x plus 3, my denominator was x minus 1. That's why I got these results. And now I can graph this function with a hole in the graph. So I plotted all my key features, my x-intercept, my y-intercept, my asymptotes, and I even drew the hole as an open circle. Well, it's nice that on this left side I could be level, go through x-intercept, go through y-intercept, and go down to negative infinity. And on the right side it was harder because we didn't have any x-intercepts here, which told me I had to be on this upper half of above the asymptote. But now, not only have to be above that, I have to go through that hole. So by the asymptote from positive infinity to the hole, and level off to the horizontal asymptote. And to be thorough, I should mark that hole as the point 3, 3. So there's that graph. This graph in blue looks exactly like, it would look exactly like this graph here, except that graph I just put on the side of the rectangle wouldn't have the hole in it. So this graph, this function I'm going to graph, I should try to factor it first. I can see I can take a 3x in the numerator. I get x squared minus 2x minus 3. In the denominator, I can take an x out, and I have x squared minus 1. Don't forget that minus 1. 3x, x plus 1, x minus 3, and I get x x plus 1, x minus 1. And I can see that some things cancel out. I see that these x's cancel out. That means I'm going to have a hole at x equals 0. And these x plus 1's cancel out. That means I'm going to also have another hole at x equals negative 1. I'm going to have two holes in this graph. So what I'm really graphing is the function. I'm going to write it in pink. When I'm all said and done with this, I'm really graphing the function 3 parentheses x minus 3 over x minus 1. This is really the function I'm graphing with a couple holes in it. Well, how do we find the values for the holes? I plug in the y value, so I'm going to plug in 0, and I get 3 times negative 3 over negative 1. I get 9, and I plug in negative 1 here. I get 3 times negative 4 over negative 2. I get 6. So my two holes are at 0, 9 is one hole, and negative 1, 6 is the other hole. Let's find a y-intercept. Well, how do we find a y-intercept? I use x equals 0, but I can't now. It's a hole in the graph, right here. 0, 9 would be on the y-axis. It's a hole in the graph. Okay, easy enough. X-intercept comes from the numerator. The only thing in the numerator with the variable is that x minus 3. That means my x-intercept would be x equals 3. I'm going to move this up a little bit. My VAs come from the denominator. The only thing in the denominator is x minus 1. So my VA would be x equals 1. And I can go to the beginning of the problem, and my leading term was 3x cubed over x cubed, which I get 3. So I have a VA of y is equal to 3. So now I could put all those points on this graph and draw what I have. Okay, you can see I plotted my holes. I have my x-intercept. I don't have a y-intercept because it's a hole. I have the asymptotes, so the right side is pretty easy. I have a dot to go through, so I'm going to do, starting at negative infinity next to the asymptote, go through the x-intercept and level off the horizontal asymptote. And the other side isn't so bad easy because I know I don't have any x-intercepts to go through, so I would have to be on the above the horizontal asymptote, but I do have dots I can go through, or holes I can go through now. So from positive infinity through the hole, through the next hole, and leveling off. So that's what the graph would look like. A little bit different. It looks exactly like what I have inside the pink, 3 parentheses x minus 3 over x minus 1, except there's two holes in the graph. And finally, we want to write a possible formula for this function. Now, again, we have to pay attention to the x-intercepts. Come on, draw. My x-intercepts, which are equal to negative 1 and 4. Right here, negative 1 and 4. My VAs are x equals negative 5 and 2. I think those were important. We have a y-intercept equal to, I don't really have a grid there. I'm going to guess 2, but I think if we recall, the y-intercept didn't really matter so much. But I do have a HA, horizontal asymptote, of y is equal to 5, and I think that did matter a little bit. So when we write our equation, I call it r of x equals, well, the x-intercepts are on top. Negative 1 becomes x plus 1, 4 becomes x minus 4. The VAs are on the bottom, so x plus 5 and x minus 2 from those two VAs. And right now, my leading term over leading term would be x squared over x squared, and that doesn't give me my HA of 5, so I'm going to throw a 5 in front here because that's what's important. And I have my result that the equation for that graph is that. Now, what would happen if I happen to throw something else? What would happen if I would throw a whole at 1, 5. Okay, well what I really need is the x part of the whole. So I really need to have x minus 1, the factored part of it, in both the numerator and denominator, because I think we just found out that a whole is caused by having things in both the numerator and denominator. So I'm going to have exactly the same equation I just did. R of x is equal to 5x plus 1, x minus 4, over x plus 5. No, that was terrible. X plus 5, x minus 2. But now I need to put this extra piece into it. This x minus 1. And this x minus 1. Because the x minus 1 in the numerator and denominator, this is what is causing there to be a hole at the graph at x equals 1. And that's what I wanted, a hole at x equals 1. Okay, so if you remember when we finished this last time, we made a little summary. So I'm going to make a new little summary. If I have a rational function, I have a numerator and denominator. I think I recall my x-intercepts were in the numerator. My VAs were in the denominator. And once in a while I have to have an HA in there if it's necessary. But now I have the idea that if I have a hole, it goes in both in the top and the bottom as factors. You get this whole R of x business is equal to this whole thing.